Tests we've talked about so far have as their goal the Familywize confidence level, or the Familywize error rate. Remember, the Familywize confidence level is the probability that all the confidence intervals in the set will be successful. And we want, for example, to make that probability equal to 0.95. Equivalently, for the hypothesis tests, the Familywize error rate is the probability that at least one null hypothesis is falsely rejected. And so we're trying to make sure that the probability that we make at least one mistake is no more than 0.05. In other words, we're trying to make sure that we make no mistakes. These methods, these goals, having Familywize confidence or Familywize error as a goal, becomes really difficult to achieve as soon as we have many, many tests. So for example, the field of genetics. Think about what people are doing with genes. Let's look at all the possible genes that could cause breast cancer and try to identify one. How many different hypothesis tests do we have to do? How many different decisions do we have to make in order to identify one gene? Let's look at all the possible ways we could answer a biological question. It becomes ridiculous to try to make a 95% probability that every interval you create covers the true value, or that none of your tests falsely reject a null. So there's another goal, a more modern goal, called the false discovery rate. And here's how it works. Suppose you do 100 tests, or create 100 intervals. And based on those tests or intervals, you have, say, 20 discoveries. So discoveries are intervals that exclude 0, or hypothesis tests that reject the null. Those are equivalent. So you do a bunch of tests, make 100 tests, and perhaps you have 20 discoveries, but then some proportion of these discoveries are errors, right? So if I say I have 20 of the hypotheses, null hypotheses that I rejected, some of those I probably rejected because really the null hypothesis was false, and some of them I rejected even though I shouldn't have. So the false discovery rate is the proportion of the discoveries that were in error. And so when we're trying to have as our goal the false discovery rate, we're trying to make sure that the proportion of errors among our discoveries is no bigger than, say, 0.05. The important comparison between these two goals is that the Familywize methods are looking at the probability that we make no mistakes, whereas the false discovery rate is looking at the proportion of mistakes that we make, acknowledging that we're going to make some. And that makes the false discovery rate a much better goal, and the methods that have this as the goal much more appropriate for modern situations where there tend to be large data sets or many questions. So again, here are our paired comparisons that we've been doing and the p-values that came from the original t-tests. Now I've ranked them, so the only difference here is we're going from the smallest p-value to the largest p-value. And now we're going to walk through the Benjamini-Hofburg method, which is the most common method, the most famous method, the first method for dealing with false discovery rate. So how are we going to do this? What Benjamini-Hofburg does is it says, okay, I want to have a 0.05 false discovery rate. So I'm essentially going to take that 0.05 and I'm going to divide it up. I'm going to divide it up such that the smallest p-value that I achieve, if I have 6 different questions I'm asking, 6 tests, the smallest p-value has as its cutoff 0.05 times 1/6. The second smallest p-value has as its cutoff 0.05 times 2/6. The third smallest p-value has as its cutoff 0.05 times 3/6. And the largest of the 6 p-values has as its cutoff 1 times 0.05. In other words, we're acknowledging that if we have a bunch of p-values, we expect once we order them, they'll have some ranking from 1 to 6. And if we use that 0.05 as the cutoff for the largest one, then we'd expect that if all the nulls are true, the rest of the p-values would be even smaller than that. In other words, if all the nulls are true, remember, we expect the p-values to have a uniform distribution. This is a related idea that we expect the p-values to be spread apart. And so the Benjamini-Hofburg method says, rank all the p-values and also use a different cutoff for each of the ranked p-values. And so if we look at these, we can say, okay, well, 0 is less than 0.0083. Right? So we're going to reject the null here. We think art is different than student. The artists have different CFMTs than the students. and 0.001 is less than 0.0167. So also we think business is different than student. And 0.002 is different than 0.025. So we're going to reject this one as well. But now we have business versus education. 0.045 is bigger than 0.033. So we're going to stop rejecting here, and we won't reject for any of the other ones as that increases. So we're going to reject the null hypotheses, say we have a significant difference for the first three, but not for the second three, using the Benjamini-Hofburg method. There's our cutoff. So again, to walk through these steps, to set the maximum false discovery rate at 0.05, if we have M hypothesis tests, we were using K when we talked about Bonferroni. For Benjamini-Hofburg, it's traditional to use the letter M. List the M p-values from smallest to largest. Compare the first p-value to 1 over M times 0.05, the second one to 2 over M times 0.05, etc. And then find the largest value such that that p-value, that ranked p-value, is less than or equal to the cutoff, just as we showed on the previous slide. And reject the null hypotheses for all the p-values up to that point. And that's what we just showed again on the previous slide. Benjamini-Hofburg is applicable whenever the tests are independent. If the tests are positively correlated with each other, also it's typically appropriate then as well. And this is a method I'd suggest if you're dealing with a lot of different questions, if you're using any kind of biological data or chemical data, I would recommend Benjamini-Hofburg. Turns out if the null hypotheses are all true, the false discovery rate turns out to be the same thing as the Familywize error rate, so that's a nice feature that these two goals do coincide in that way. And if some of the null hypotheses are false, it's more powerful to use the false discovery rate procedures than the Familywize error rate procedures. We're more able to actually have discoveries. We're not going to be so conservative that we never reject any nulls if we're using Benjamini-Hofburg.